I'm going to present a brief overview of batch reactors and some of the important aspects of batch reactors and discuss a little bit about scale-up of batch reactors. Essentially, a batch reactor is a container in which we stir what's typically a liquid phase, except on a very small scale, batch reactors are going to be liquid phase. And one of the important aspects to consider a batch reactor is that it's a closed system. What I mean by a closed system is we're not adding new material to the reactor, we're not removing material. In most cases, it's liquid phase, and so we often make the assumption that the system is at constant density. In other words, the volume is not changing. With time, the mass is not changing. An important aspect in order to model a batch reactor is that the system is well mixed. In other words, the stirring is sufficient, the baffling in the reactor is such that there are no gradients. So we have no concentration gradients, we have no temperature gradients. So if we had a reaction such as A goes to B, what this means is concentration of A and the concentration of B are uniform throughout the reactor. So that means spatially uniform. And likewise, the temperature throughout the reactor is uniform spatially. But all three of these change with time. So concentration of A, concentration of B, and in general, the temperature change with time. Of course, to have reaction, we want these to change with time. So they're changed in respect to time, but not spatially. And so batch reactors are used on a large scale. They actually make more different products than any other type reactor. They don't make more volume, but they're used for a number of reasons. One is when we want to make something on a small scale. In other words, we're not going to have a continuous process, something that's expensive. Sometimes we have a new process. We want to determine how we're going to carry it out, so we initially do it on a small scale, a batch reactor. If we have very expensive reactants, products, then a batch reactor might be appropriate. If we have a very long reaction time, then instead of a continuous flow reactor, a batch might be. And then if we have the case where contamination can affect our product, for example, in fermentation, then a batch reactor is appropriate. The other use is batch reactors can be used to make multiple products sequentially. So we carry out multiple reactions where we might run the batch reactor for a week, several weeks for one reaction, clean it out, now run it for another set of reactions. So an important aspect of batch reactor, in order that the temperature be uniform, for example, is that the stirring is good. And if we're interested in, say, an isothermal reaction, heat transfer is very important. The reason is that most of these reactions that we're going to carry out on a large scale tend to be exothermic. In order for delta G to be negative, typically delta H is negative. And so for a reaction to take place at a reasonable rate, that heat needs to be removed in some cases, depending on how we're going to run a reactor. And so we can imagine actually running three different arrangements of batch reactor. One would be to run it isothermally. By that means we have some cooling jacket in this two-dimensional representation. A coolant flows in one side, out the other. We could use a phase change coolant to keep it isothermal. So if we have sufficient coolant, we could run it isothermal. The other extreme is we insulate it completely and let it go to its adiabatic temperature. In other words, there's no heat transfer and all the heat of reaction goes to heat up reactants and products. And then an in-between case is where we have coolant, but it's not such as to keep it isothermal. Isothermal here means that the temperature doesn't change with time. We're assuming in all three cases the temperature is uniform throughout the reactor. What matters then, and why this becomes particularly important, is when we want to scale up. So let's look at, again, the two extremes. So this is the isothermal case, meaning the temperature doesn't change with time. And we go from this small scale to something that, the way I've drawn this, if we think of 3 dimensions, it's about 400 times the volume. then we should be able to use the exact same conditions, as long as stirring is sufficient, to go from this small scale to large scale. The equations modeling it would be the same. So this scale up should be direct if we can maintain it isothermal. The other extreme, of course, is adiabatic. Again, this 400-fold increase in volume. This also should be scaled up directly as long as stirring is sufficient. The same equations that work for this small reactor are going to work for the large reactor. And so when I say the same equations work, what I mean is that the concentration of A and the concentration of B, if we were to plot them versus time, they're going to be same for the small reactor and for the big reactor. And likewise, adiabatic, if I plot concentration of A, concentration of B, and the temperature versus time, they will be identical, again, assuming the stirring is sufficient. It's the in-between case, the non-isothermal case, where temperature changing with time is not adiabatic, that is different, and we have to be more careful in terms of scale up. And so the idea is, let's look at non-isothermal, which means temperature's changing with time, but we have some heat transfer. And let's look at the case of comparing a lab reactor and some large reactor. Let's say the diameter is a factor of 10 larger. If I look at volume, and let's not worry about units, just say in some units the lab reactor volume is 1. If we're going a factor of 10 in diameter, this is 10 cubed in volume. And if we look at the heat transfer area, let's call this in the lab scale 1, then this would be 10 squared. In other words, we've increased the volume much more than we've increased the heat transfer area. And what this means then is heat transfer is going to be more difficult to maintain the desired temperature profile that we're interested in. Of course, we can see why the volume goes up. The volume is going to be, in this case, if I make d the height and d the diameter, so the height times pi d squared over 4 would be the volume. The area would be the height times their circumference, and the way I've drawn it, there's also heat transfer on the bottom, which would be heat transfer area of pi d squared over 4. In both cases, you can see this is as d cubed, this is as d squared. And so there are a number of issues then when we try and scale up. So we just discussed that heat transfer can be more difficult because the volume goes up much faster than the area for heat transfer. Mixing can be more difficult on the larger scale. When we start this reactor up and we have to heat it to a reaction temperature, for example, or we have to add all the materials and mix them together, the startup is going to be longer as we go to the bigger scale. Also, typically the reactor materials are going to be different. In other words, we might actually on a small scale use a glass reactor, and a large scale metal reactor we have to worry about various things such as reaction of metal, catalytic properties of the metal. Finally, and very briefly, let's just look at the mole balance for a simple batch reactor with one reaction. So simple A goes to B reaction. I made it second order. And if I write down the mass balance where Na is the number of moles of A in the reactor, how they change with time is equal to the rate of reaction, which is moles per time per volume, times the volume of the reactor. And the way for the system I've picked, okay, Ca squared times volume. Now, if it's liquid phase, we assume constant density, then the volume is constant. So number of moles is just a volume times the concentration of A, which I can write this way. And you can see the volume disappears. And so we can then calculate what happens during reaction independent of the volume. This is assuming that the temperature change is not so large that the expansion of liquid is significant and affects the concentration. This is just a brief overview of batch reactors. There are other screencasts that go into more detail on the mass balances and then solving the mass balance.